Okay guys, let's understand Vant Hoff factor I. Formula for Vant Hoff factor I is 1 plus alpha n minus 1. Now this alpha is degree of dissociation. Alright, number of moles dissociated divided by total number of moles taken. Now, prior to getting into understanding I, we have got to understand what are weak and strong electrolytes. Now, if we are talking in terms of weak electrolytes, it could be weak acid or it could be weak base. Now, first of all, electrolyte are those where the molecules dissociate into anion and cation. Alright, whenever put in water. Alright, now, in case of weak electrolyte, let's know some of weak acids. Weak acids are all those fatty acids beginning from formic acid, acetic acid, butanoic acid, propanoic acid, and all those fatty acids are weak acids. Hydrocyanic acid, HCN, is weak acid. H3PO4, weak acids. Alright, these are weak acids. Now, if we talk in terms of weak bases, it's ammonium hydroxide, and all hydroxides of D block elements are all transition element hydroxides are all weak bases. Alright. And finally, what are weak electrolytes and strong electrolytes? Weak electrolytes are those which hardly dissociate. Weak electrolytes are those which dissociates hardly, whereas strong electrolytes are the one which dissociates completely into cation and anion whenever put in water. Alright. Having understood weak acid, weak base, and weak electrolyte, let's proceed in understanding Vant Hoff factor with weak electrolytes. Now I have chosen here phosphoric acid, a weak acid. Now phosphoric acid dissociates, giving you 3 proton and 1 phosphate ion. Altogether 4 ions are obtained. It is number of ions obtained are 4. Okay, so what was this N? N was number of ions obtained after dissociation. So we got the value for N, which is 4. And degree of dissociation is number of moles dissociated upon total number of moles. Now here, it's mentioned that it dissociates 10%. Means if there are 100 moles of phosphoric acid, out of that only 10 moles have dissociated. So alpha is 10 over 100, that is 0.1. So we got alpha 0.1. We got N is equal to 4. Now formula, substitution, and what we end up is 1 plus 0.1 in bracket N is 4, 4 minus 1, so 3 into 0.1, that becomes 0.3, so 1 plus 0.3. So Vant Hoff factor comes to 1.3. Mind you, always the I value would be greater than 1. Alright, I value would always be greater than 1 for dissociation. Now let's understand for strong electrolyte. Now let's understand some of the strong electrolytes. Strong electrolytes in case of acid are hydrochloric acid, sulfuric acid, nitric acid, and so on and so forth. And strong bases are alkali, alkaline metal hydroxide, sodium hydroxide, potassium hydroxide, and all those hydroxides are strong bases. So these are all strong electrolyte. And as I mentioned, strong electrolyte in the sense as soon as you put in water, they dissociate into anions and cations. The example that I've chosen over here is sulfuric acid, a strong acid which dissociates to give 2 H plus and 1 sulfate ion. And obviously strong, so it dissociates 100%. If 100 moles I take, 100 moles dissociates. So 100 over 100 is equal to 1 as 100% dissociation. So this alpha would always be 1. Keep it in mind for strong electrolytes, because as soon as you put it in water, an aqueous medium, it dissociates totally. Alright, okay, let's get into formula now. So this is the formula. So here degree of dissociation is 1 and number of ions generated is 3. So what I do is I just don't do that. There's a purpose why I'm not substituting it over here. Now, so I don't substitute N over here. So what I do is I do this 1 I have substituted, and when I open up, what I find is 1 and minus 1 gets cancelled and N remains. Therefore I is equal to N. So what do we gather from here? We gather from here that in case of strong electrolyte, no need of doing all this calculation. You just check the number of ions and put there that. So now let's substitute the value and check it out also. Now see, what I do is I put in over here N is equal to 3. Alright, I have put in 3. So 1 plus 3 minus 1. So that gets cancelled. So 3. So 3. So I is equal to 3. So whenever you are given strong electrolyte, please don't go in for any calculation. Straight away you can put it as equal to number of ions dissociated. Fine. So that's for strong electrolyte. So for strong electrolyte and weak electrolyte, for dissociation, we found the value was always greater than 1. Alright, so that's what I've written over here. Now in case of strong electrolyte, Vant Hoff factor is always equal to number of moles dissociated. Alright, so we got 2 moles of this, 1 mole of this, so number of moles dissociated is 3. So 3 is the value. Alright, okay, now let's check out for association. Okay guys, now let's understand association. What happens for association? Formula also changes a bit. I is equal to 1 plus 1 over N minus 1 alpha. This is the formula that we have got to use whenever we are tackling association. Now acetic acid dimers in benzene. Dimers means it 2 molecules combines together to form a dimer. So it forms a dimer in benzene. It's given that it dimerizes to the extent of 10%. Alright. Now, what is alpha? So obviously alpha becomes 10 upon 100, that is 0.1. Only 10%, so 0.1. Now, what do? We substitute alpha, we have substituted, and dimerization how much? 2. So N is equal to 2. So we substitute that N over here. So on substitution, half minus 1 becomes minus half, that is minus 0.5. So that is minus 0.5. So minus, I took it out over here. So I've jotted down here minus 0.1 into 0.5. It gets to 1 minus 0.05. 0.5 multiplied by 0.1 is 0.05. So the value that we get is 0.95. So value of Vant Hoff factor is less than 1, that is 0.95. So what do we conclude from this? We conclude that always for association, whenever there is molecular association, at that time Vant Hoff factor would be less than 1. Alright, so in association, Vant Hoff factor would be less than 1. In case of dissociation, whether it be weak or strong electrolyte, value of Vant Hoff factor would always be greater than 1. And another thing that we saw is strong electrolytes dissociates totally, whereas weak electrolytes dissociates weakly. Alright, so that's how the calculations are to be done for Vant Hoff factor. Another significant factor that I told is whenever you are dealing with strong electrolyte, whatever are the numbers of dissociated ion is the value of I, Vant Hoff factor. So please don't waste your time utilizing the formula and calculating. Directly jot down whatever is the number of moles. Okay.